So moving on to the Q&A session. So the first question is for Professor David, and it is, can pincer ligands be used in combination with maleic anhydride to generate the palladium complex?
Yeah, that's a really good question. So we've looked at a number of like multi-dentate phosphine ligands. So as part of the cross-coupling work, we looked at things like Xanphos, DPPF, DPP, et cetera, et cetera, et cetera. We haven't ever looked at specifically pincer type ligands, so like PNNP or POCOP or things like this. I think certainly from everything that we've seen, the coordination should work fine. Phosphines are, seem to really be thermodynamically preferred in these complexes. That diamine will get out of there for sure. I'm not sure if we would be able to do the subsequent, say, like carbon metallation to do like CH activation to make like a PCP complex because we're at palladium 0. But certainly any like L3 type pincer, like a PNNP, PNP, that should work pretty well.
Yeah, thank you for your response. So next question is for Professor Stelios. Does the hardness or softness of the reactive center or the nucleophilic group impact the asymmetric outcome of these allylic functionalizations?
Yeah, let me unmute myself. That's a good question. I mean, there's definitely an impact, not only on the selectivity, is there an impact on the reactivity as well. So hard nucleophiles is usually don't work. Okay, so it's usually soft nucleophiles that work. So there also needs to be a good balance between the electrophile and the nucleophile. So I hope I answered the question. But for the selectivity outcome, I mean, there's a big substrate dependency, right? So this is something that needs to be evaluated case by case. But for reactivity, there's clearly an impact whether you have a hard nucleophile or a soft nucleophile. There's a clear impact on the reaction feasibility.
Thank you for your response. The next question is for Professor David. So, what are the thermodynamic factors responsible for the better efficacy of the single component catalyst compared to the other catalysts?
Yeah, it's a really good question. So in principle, no matter whether you're forming something in situ or you're going with a single component catalyst, you should get to the same thing in the end. I mean, most palladium chemistry sort of relies on this fact. I think what we're able to do, and I think especially in AAA chemistry, this is really important, is that by preforming the catalyst, we don't need to worry about things like background racemic reaction. We don't need to worry about formation of other kinds of like coordination modes for the complex. So again, just back to that Guy Lloyd-Jones work, with palladium 2, you often observe phosphorus oxygen coordination with its trosis ligand, so that oxygen of the carbonyl from the backbone will also coordinate to palladium. And so in our case, I think the key sort of factors with palladium 0 is that the ligand metallation is very fast because palladium 0 is just a more labile system. The ligand substitution rates are a lot faster. And the thermodynamic preference between the soft palladium 0 center and the soft phosphines means we have really strong thermodynamic driving force to form that complex. Once the catalysis kicks off, then it should just, it'll do what it does. But I think the key thing is going in there with the complex already formed. We don't have to, again, worry about other sort of speciation during that in situ process, especially using palladium 2 as the in situ precursor.
Thank you for your response. The next question again is for Professor David. Have you attempted to prepare the corresponding nickel 0 complex? And if yes, is it stable and does it exchange ligands easily?
Great question. Yes, we've attempted it, and no, it's not stable. What we think is happening in that case is that maleic anhydride is actually known to undergo oxidative addition to nickel 0. There are some older papers in nickel chemistry with anhydrides in general will do oxidative addition. We've found a way around that, and so we're just about to submit a preprint on a nickel analog of these. It's not the exact same complex, but yeah, nickel's a little more capricious, but yes, we're about to put something out on that. So it's a great question.
Thank you. The next question is for Professor Stelios. Can this strategy be extended to diastereoselective synthesis, like to chiral centers?
You could the easy answer is yes. If you like, for example, if you take an cinnamyl acetate, alpha phenyl cinnamyl acetate, for example. So you will generate two contiguous stereogenic centers. Then, if you're lucky, you will control this, both the diastereoselectivity and the enantioselectivity. I think the better way to go for diastereoselectivity is to switch to iridium, though.
Sure. Thank you for your response. And I think the next question is for both of you. How effective is the scalability of these reactions, and does it have any impact on the overall enantiomeric axis?
I mean, so it depends how you define scalability, right? I mean, if you talk to David, who's an ex-process chemist, he's going to talk about very, very large scale. If you talk to me, a gram scale is already a scalability. I mean, to be fair, we did some scale-up reaction on gram scales. Phil and Manolis at Scripps did 10 times that, so it is scalable. I think if you manage to go down in catalyst loading, which is the case, for example, in the hydantoid that David is showcasing, and if you think about it, we use 7 milligrams of catalyst for a couple grams of substrate, right? I mean, for 1.3 grams of product formed at over 90% yield. So yes, the answer is yes. It is scalable, but again, you have to be very careful. And that's the whole point of this project with David, is to make this technology available for process chemists. David, did I answer the question?
Yeah, I would say, well, our next task is to do it on like half a kilo, and then we'll talk about scalability from that. But yeah.
Thank you for your response. Yeah, so we can, I think, move to the final question for the day. What is the effect of the nature of the palladium catalyst, like cationic, anionic, or neutral, on the reactive outcome? I think this question is for Professor Stelios.
Well, that's more a question for David. Because no, I mean I'm gonna go in a different route. I mean, you talked about scalability, impact on selectivity. One thing which is problematic with palladium DBA is concentration, right? If you go too concentrated, then you have oligomerization issues, and basically you kill your reaction. So that impedes scalability, for example, like if you really want to go on large scale. Now we've never worked with other palladium sources than palladium DBA, the palladium dab from David, or the chloroallyl complex. So I don't know the answer.
Yeah, just a quick follow-up on that. So there, in terms of the precursor, because we're going in with palladium 0, and what we think actually happens during the reactions, the maleic anhydride is removed by action of the base or the nucleophile. And so we'll get into whatever sort of reaction manifold is needed, whatever kind of mechanism is needed for that particular AAA reaction. There is one other single component AAA precatalyst with the TROS-type ligands that was reported by Guy Lloyd-Jones, I think in like 2003 or 2004. That is actually a cationic allyl complex. And so that is another entry point. But our goal with these kind of precatalysts is to sort of be as general as possible, so that whether or not it's a neutral palladium or a cationic palladium or the anionic palladium type of reaction mechanism, the precatalyst is still able to get into the active form for any of those. Yeah.
Sure. Thank you so much, Professor David and Professor Stelios, for your responses. Over to you, Nia.
Thank you so much, Manish, for moderating this Q&A. And I would request Professor Stelios and Professor David to please put on some concluding remarks for our audience.
David? I mean, I'll start. I mean, it's nice. It's nice. I mean, I went through the website. I went to look at previous science talks, and I think it's a great idea. I mean, there was over 120 participants earlier. I can see that my dad is participating as well. So I think it's a nice way to share. I mean, David is in Canada. I'm in Europe, and you guys are in India. And how big is this window? You know, this is amazing, and I really appreciate the invitation.
Thank you.
Yeah,
so
no,
much.
I absolutely echo those comments. My family is asleep, so they're not on the call right now. I actually need to leave to go and wake them up now. But I just want to close by saying this work, would not have been possible without this, global collaboration. And it's been a really, really fantastic learning about AAA chemistry, learning about natural product synthesis areas that I'm not an expert in. And so if there's one thing that I can say, just in general, is like collaborations are fantastic, and get involved in as many of them as you can, especially if you can find a good collaborator like Stelios.
And it's also, I mean, I'll add something. I mean, this is a huge collaboration between two academics. Let's not forget that there's also an industrial partner. And I mean, without them on my side, it would have been really, really difficult. And they're very, very eager. I mean, it's a very nice. It's always bubbly, every time we have group meetings, there's a lot of new thoughts and new ideas that come out, and it's really nice to also have the angle from the industrial partner as a process chemist, because we need to make this chemistry useful for everyone. So hopefully we're managing.
Thank you so much, professors. And this brings us to the end of today's session. We hope that you thoroughly enjoyed your broadcast, and we invite you to view the edited recordings from the past events in the ACS Science Talks library. You would receive a certificate and a short survey to fill your experience with the ACS Science Talks. So on behalf of all of us at ACS, thank you for joining in today. We hope to see you again soon for more ACS events. Until then, stay safe and healthy. And thank you so much, Professor Stelios and Professor David, for your wonderful lectures. And thank you, Manas, for moderating the Q&A session, and the ACS team members. Thank you so much.
Thank you so much.
Thank you.
Thank you.
Thank you.
Great. Yeah.